Okay. Okay. So this is the teaching plan for this course, e.g. 823, Numerical Methods 1. So I understand you'll be taking Numerical Methods 2 in second semester. And here you have my details, including my email and phone number. And then we have a brief background. So this is an advanced course that focuses on the application of computational methods. And that deals with solving mathematical problems using numerical techniques. And the major highlights here are, methods for solving ordinary differential equations, boundary value problems. So meaning in considering the ODEs, we want to look up the initial value problems, and then we'll try to address the boundary value and characteristic value problems. Then we'll look up the nonlinear equations, then the partial differential equations. We'll also consider spline functions and approximation of functions, numerical integration, and then I think that's about it. Then we'll also look up techniques or methods for, computation in terms of modeling some of the software. So we may want to look up MATLAB and Python, Python programming. So the core objectives of this course, well, is to equip students with the theoretical foundation and practical skills needed for applying numerical methods to solve ordinary differential equations and boundary value problems. So why are we particular about differential equations? Well, that will become clear shortly. I hope this class is interactive. Then we'll also explore applications of spline functions and, well, the objectives cut across the content of this course. And the idea is that students are able to apply these methods in solving problems, real life practical problems, okay? And I think that's about it. So we don't just want to look up these mathematical models. Why do we need to use these methods? Why do we need them in the first instance? So I think those are some of the questions we are going to be answering, okay? And then here we have some resources. So it's just that, well, interestingly, I get to take any course I'm assigned. So do I really have any specialty? Well, I don't know. Although electronics telecommunication, but whatsoever my boss says I should teach, I just get to teach. Okay, so here I have I had to introduce a new playlist in my YouTube channel. So so you could subscribe. So once you go to YouTube and make a search, just type in Augustus Ehireme, then you should see the channel pop up. You could subscribe. I'll encourage you to subscribe because I'll be updating the notes, okay? So there are some other courses you may be taking in the playlist and some you may not. And also, you may want to refresh your memory or memories. We are many now. I understand some of us may have left the educational sector system for quite some, for a long time, quite a number of years. Probably you went on to set up your businesses and you feel fulfilled financially now, and you feel, well, there is a gap. You want to be able to control some other systems, so you need some higher degrees. Right? For some, they need higher degrees just to get going with their plans. But whichever way, some of the resources in the playlist, different playlists, may be helpful in refreshing your memories or memory. And now for the numerical method, there is a playlist. So if you're able to search through, you will see an introductory video that have provided a brief overview, and as well as detailing some of the application areas. So regardless of your discipline or area of specialization, these numerical methods or techniques could be used to address problems in different domains in your discipline. Okay. And then there are a few materials. Well, this is not exhaustive anyway, so I'll suggest you look up other reference materials. So we have the Zarowski CJ, an introduction to numerical analysis for electrical and computer engineers, an interesting book published by John Wiley and Sons. And also the Esfandiari RS, published in 2017 by CRC Press. So that's numerical methods for engineers and scientists using MATLAB. And I think there's another material that uses Python. So you want to look up these resources, and then the assessment. It's expected that you meet up with 65% attendance. Well, so while we're in class, just try to drop your details. I think that will be one good way we'll be able to learn or know ourselves. So you want to drop your details in the chat room, your name, probably your matric number, your option, and if possible, what you do. Okay. So we just have that as our record, and we could keep that for attendance while we're in class. And for the evaluation process, we should be having about that 30-70 or 40-60 average. So continuous assessment should take about 30 to 40% of the total score. And we'll decide on that if we're going to be having assignment or written assessment and the likes, quiz and all of those, probably projects. Okay. Yeah. So at this level, I usually prefer projects. Okay. Because that helps accumulate your continuous assessment. And then we are able to tell that you've been able to apply these techniques. Okay. So when you're able to look up the overview, the note on the overview on numerical methods already published in the YouTube channel, you may be able to identify one or two problems you would love to address relative to your field or discipline. I'll suggest that you go on to develop that idea and put it up in a paper format, which could be published, okay? And at this point, you don't have to worry about your tutor's discipline, okay? Yeah, I may end up not participating in the publication process. We may end up recommending somebody in your discipline, in the system or outside the system, to collaborate with you on that paper so you could publish it, but it will be assessed. So make it part of your assessment, maybe 50% or more of your CA, okay? So there you are able to conduct a little research, run MATLAB code to address that problem. And then we move on. So then we have exam, which takes about 60 to 70%. Now, here is that slide, but there's something I want to show. Okay, now, these are some of the application domains, okay, which we have, for instance. So for the ordinary differential equations, I don't want to run through them in detail, but you could look up the uploaded note. Now, for instance, for the ordinary differential equations in communication engineering, we could use SIM to address problems in signal transmission and filtering systems. So let's assume you want to make this your assignment. So you want to pick this up, and then you are going to be addressing this problem using the ODE. So probably you want to design a filter using the numerical techniques. Okay, perfect. So you're going to develop that into a full-fledged paper for your CA. Okay, so if that's good, that may end up taking about 60% of your continuous assessment, while we could now take some quiz and probably written assessment to take up the remaining 30 or 40% of your CA. Okay, and this should run for the next 1 month. So we know, this is hands-on, okay? And then you could look up some published articles to see how it is if you've not done that before. Then we'll also measure up your progress report to be sure you are doing the right thing. So once that is settled and you've been able to come up with that, then if it's not in my field, if it's not in the communication field, or well, it doesn't matter, we are using numerical methods, so I should be able to look it up now. Okay. And we could also invite some expert in your field to look up the technical details. Okay, let's assume you are doing something in machines or drives or power systems. So, and then I think the next slide has something on. Okay, so for control, these are some of the things you could do with ODE and for machines and drives. So you could do DC motor transient analysis using ordinary differential equations. So let's assume you decided to do that as part of your project for your continuous assessment. So it means that while I look up the numerical method applied, how you were able to use that to address the problem, now to validate the technical details, I may have to give it to one of our lecturers in drives to look it up. So if it's good enough for publication, then you could collaborate with that person.
Sorry, sir.
And then publish.
Hello, sir.
Go ahead, please.
Yeah, sorry. We could not hear you properly, sir. We don't know if I thought we can help us
Mute
increase the volume.
your video. Mute your video. Enter audio.
Okay, sir.
Okay. But can others hear me?
I can hear you clearly, sir.
Yes, you can hear you, sir.
Clearly.
Yes, sir, I can hear you loud and clear.
Okay.
Audible.
Okay. So,
Okay, sir.
And who knows? That may just solve your penultimate project work. Okay. So, if what you've done is good enough and we are able to figure out someone in your field that picks it up, then we can as well say from this course, you've been able to address a problem you could make your final year, your main research work. And that just solves the problem and everybody's free from some kind of delay or crisis, okay? So the bottom line is the methods you're going to be learning here will help in honing or better still developing the skill set to model physical problems mathematically. I think that is the idea. That is the goal. Is that okay?
Yes, yes, sir.
Okay. So on this, any question, please, before I move on? So if there's anything you are not clear about, or you feel there are some other things we need to talk about. Okay, so this is a P here.
Yes, doctor, can you hear me?
Yes, I can hear you.
Yes. Thanks, sir. Thanks for all the luminaries you are giving to us. We know that you have a good time with you. So God bless you, sir.
Bless you too.
So I want to ask, our lectures, will it be all true? Can I proceed?
Go ahead, please.
Yes. Our lectures, will it be all online, all true, or will it be half online or half physical?
Okay, so what exactly will you prefer? So let's hear from you.
No, it's taught to the class. It's not based on you. No, like power systems.
Mm-hmm.
Hello, sir.
Yeah, I can hear you.
Like in power systems, his own is at least he has started with physical. So we want to know there are some things that maybe online we'll be able to grab. At least physically we'll be able to interact again with you. And so if it be online, so when can we meet you again personally to interact with you physically, so that some little you might be having can be resolved?
Okay. That's not a problem. We could always schedule. Okay, if we have to meet, then we could schedule on my consultation days. But if that won't be convenient for you, then we could schedule an online session any time of the day. Okay.
Okay. Yes.
So interact.
Will you be kind enough to give us your maybe contact, because it's not shown?
Yeah.
what you have is the email address. Can we interact with you?
Why not? Have
Phone?
you joined the WhatsApp group?
Yes.
Yeah, that's my contact. Just check the admin.
All right.
That's my contact. So you can. I also displayed it not too long. So I'll also upload this lecture note. So this video, so you are able to look it up again and again. So that's just the essence. So my thought is,
All right.
Yeah. So my thought is, if we end up having physical classes while describing some of these details, we may not be able to record them. But if we have them online, then we could always play back, right? So if it's uploaded, we could always play back and then catch up. But notwithstanding, we will need some physical classes where we are able to actually interact. So we don't want to rule out the social factor in the learning process. Okay? So I think, yeah, we want to do beyond online, so we are also able to engage physically. Okay, so I think we need that for the to keep the social balance, right? What do you think?
All right, thank you, sir. Many thanks, sir.
That's nice.
Okay.
Yes, Doc, that would be nice, sir. Thank you, sir.
Okay, so like I already mentioned, we've been able to look up the topics we are going to be considering in this course. So, and the first of which is numerical methods for ordinary differential equations. So before I begin, I'd love to know what you know about ODEs coming from your background. So over to you, class. So tell me, what do you know about ODEs?
Yes. Ordinary
differential
equations. Yes. ODEs are just, they are equations that define the performance, let me say the performance equations of systems and devices. Like in electronics power system, there's some or controls. When you want to analyze some systems, they are defined in differential equations, which you need to maybe integrate or use any other method to solve.
Perfect. Interesting. So used to model past systems. Okay, their behavior. So any other idea?
Okay, yes, sir. Yes, sir. So I think ODs are actually used to model the relationship between different subunits of a system entirely, and also they actually involve just only one independent variable in their equations of expressing such.
Okay. And what is that independent variable?
The Y and the X.
What is
the independent variable most times is denoted by X, but it could be arbitrary.
Okay, the independent variable. Okay, so I think this is a good place to start. Let's get busy now. So we're going to start with what you just said. So, okay. So just need to write this.
Doc, good morning, Doc. In addition to that,
okay, go ahead.
Richard speaking.
Go ahead.
So in addition to modeling, it also can be used for predictions.
Okay, can be used for prediction. Okay, so we've had modeling, we've had prediction. Okay, and then we talked about independent variables. Okay. Okay, and someone said X, right? Isn't it?
Yes, sir.
X. So what can we, now what is X? So that's my question. What is S?
Talking about non-variables.
What?
X is the input stands as the input.
Okay. X serves
In
as
the input, yeah, it stands as the input variable
the input variable.
or the input signal to the system, which you need to perform some operations on to get the output.
Okay. Perfect. It said is the input variable. So let's assume we have a system. We say this is X. And then what we get out is what?
Y.
Is Y. So this is a system, right?
No.
So now what we are trying to describe now is we have dependent and independent variables, right?
Yes. Yes, sir.
So variables. Now this X is supposed to be the same as what? This Y. Y is supposed to be what? What is Y?
Y is the output.
F of X. F of X.
Okay, someone just said F of X, right?
F of X.
Y is F of X. Okay. Now, we have quite a few details to clarify now. Okay, so, and now if we say Y is F of X, then what is Y prime?
That's the derivative of Y.
Okay,
the first derivative of Y.
So we can answer this is F of X.
F prime of X.
F prime.
F prime of X, right? So
yes,
that will be F prime of
F prime of X.
Okay, F prime of X. Okay. F Y prime you said is F prime of X. Wow, this is smart. Okay, very smart. Now, when it comes to system modeling, we have the dependent variables, and then we have the independent variables. So it means that for us to have a dependent variable, it must depend on an independent variable. Now, this is the first point of clarity I want us to establish our thinking from. Now, in system modeling, the independent variable could either be time or space. I don't know if that is clear. It could be that the time, t, or it could be space. Now, when the independent variable is space, x, can we really say it is the input? So that is where the description annotation becomes confusing. Because my input should be a function of the independent variable, say s of t. Now, where I have to deal with space, then I want to say s of s. But I now need to know the difference between my input and my independent variable. Because x and x are not the same. S is not equal to x. Is that clear?
No, not really.
Okay, not really. Good. Now, I think because oftentimes when you look up a couple of materials, you see that the ordinary differential equation is described, say, S, Y, f of x, y, or f of t, y. Right? Is that clear? Now we are going to be playing with this. And there's usually the misconception when we come to modeling. So when we come to modeling, we know that we want to represent a system whose response is changing with respect to time or with respect to an independent variable. It could be changing with respect to space or with respect to time. Okay? That's what makes it a system. Be it a power system, be it drives, be it machines, be it electronics, be it communication devices. Now, regardless of the devices, we now say, well, that forms the system we want to analyze. And anything can be the input. But the bottom line is that input must be a function of some independent variable. I don't know if that is making sense yet.
Yes, I get it.
Yes.
Yes, you are getting it.
Now, if that is making sense, then can we say that X is the input is the same as the independent variable as we mentioned earlier?
Yeah, it's an independent variable.
Is it?
Is the input,
Yes.
Can the input be an independent variable?
No, it cannot.
No, it's no more, and because it's a function
Of.
It's
a
it has
function.
become of another.
Yeah. So that I think that's the first thing I want us to get cleared in describing systems. Okay? Because now we are dealing with ordinary differential equations. So we need to know the components or the parameters we are dealing with. Okay? And regardless of our discipline or whatsoever we want to model, we see everything as a system. And whatsoever comes into that system, we see it as a signal. Isn't it?
Yeah.
Okay, so let's wipe this. So we are still on ODEs, right? So the bottom line is everything we are going to be dealing with boils down to signals and then systems, right?
Yes.
Now, these systems could be power, machines, it could be drives, it could be electronic, it could be communication. Okay? The system. Okay? But what is a signal itself? Now, if you look up the playlist on signals and systems, there we mentioned that signal is an abstraction of any measurable quantity that is a function of one or more independent variables. And such variables could be either time or space. Why a system is also an abstraction, okay? And in describing the system being an abstraction, we say it takes input and produces output. So the system is an abstraction of anything that takes in an input signal, operates on it, and then produces an output signal. So one thing I want to ask you is this: can systems be signals?
Well,
can systems be signals?
Well, in my own understanding, a system can be a signal when where a whole system is a cascade of several other systems, whereby the output from one system is an input, serves as an input to another system. So in that case, that system is a signal producer to
Okay,
the second one.
the fact that it is a signal producer to the second one, this is what you mean. We have a cascaded system.
Yes, sir.
Okay, so the fact that it is a signal producer to the second system, does the system now become a signal?
No.
Does it?
I think so.
Okay. Now, because I need us to get this through, because this is going to lead us to differential equations and then to modeling. So we need to get the perspective. Okay, so let us start all over. What is a signal? So we are saying that a signal is the abstraction of anything. Okay, so let us assume I decide to speak with someone. So my speech at that point in time is a signal, right? But
Yes.
yeah, it's a signal. But I am the system. I'm the one producing the signal, right? So
Yes.
I have my speech. Okay. So let's assume I call this S as my signal. But will you realize that someone very close to me can hear what I say clearly, and someone very far away may not be able to hear me clearly, right? So it means that something is happening to this speech with respect to time or space, right? So it means that as this signal begins to travel over time, within the time frame, it is attenuating. So I can either describe it with respect to time, or better still, I can also describe this signal. If, for instance, my space is X, I can also describe this signal with respect to space. That there is a difference in the audibility of my speech signal with respect to location. Someone close to me can hear clearly, then someone close to me may not be able to hear clearly. So that now borders on, do I want that person far away to hear clearly? So I may want to amplify. So that brings us into another system design. So I want to design an odd what do you call it now? An amplifier. Okay? An amplifier to amplify the signal, right? So the point is this: if I should create an amplifier, does that amplifier become a signal or is a system?
It's a system.
It's a system.
It's a system.
Okay, now it is a system. That's where I'm going over. But the point is that amplifier, so this is me, this is the amplifier. That's why it's a cascaded system. It's an amplifier. So this is my signal, S of t. So this is me generating it from somewhere, which is part of me, and this is S of t. So this signal goes into this amplifier, and then probably this is how the signal is. And now I can see that the signal now looks something like this. The bottom line is this amplifier is a system. And this is where our modeling ideology comes from. Okay? We must be able to tell which is the signal and which is the system, be it a voltage signal, current signal, or whatsoever. Okay? So that signals cannot be systems. The same way systems cannot be signals.
It means something needs to be introduced.
Yes, something needs to be introduced. Okay? Now, the reason is that systems cannot be signals because systems are processes that takes in signal. Okay? They are processes. So these systems, they are processes. So processes can take up signal, they act on it, and then they produce the same signal. Or we could corrupt the signal. Probably our intention is to corrupt the signal. So the same thing happens in your power system plants. So there's a point of low voltage generation. There's another place of high voltage generation, isn't it?
Yes.
Exactly. So, but for you to be able to do that, there are systems to do that. Now, those systems are processes that have been designed to operate on those signals. So hence, the signal may vary relative to some parameters that are like constant. And those parameters that are like constant are the independent variables. Time is time, space is space. But my dependent variable changes, but we call it independent variable. So why am I saying they are like constants? So why am I saying they are like constants? You know, so the bottom line is this. Let's assume I have my time scale. T0, T1, T2, T3. Now, these time values, they are constant. They are not changing. But at that instant of time. But by the time I move from one time instant to another time instant, then I'm literally changing my location and position with respect to that time, so it becomes a variable. Okay? But the idea is that it is independent of what I'm considering. So it means that what I'm considering cannot really change the order of my time, but the order of my time can change what I'm trying to observe. Is that clear?
Yes.
Yeah, so that's why your signal at this point becomes the dependent variable. So the measurable quantity we are observing as a signal is a dependent variable. Okay? So that's why we say a signal is an abstraction of any measurable quantity that is a function of some independent variables. But the measurable quantity we are dealing with is a dependent variable. Okay? Now, since that dependent variable is changing with respect to an independent variable, that brings us to the time rate of change. That is where the dx, the t comes in.
I didn't get the last point.
Okay. I think, okay. Okay, now let's, okay, let's change the color. Now I said, we already understand that the signal is an abstraction of a measurable quantity, and this measurable quantity is the dependent variable, right? You got that?
Okay. Yeah.
Now, that dependent variable is a function of an independent variable, okay? So it means that this dependent variable is literally changing with respect to the independent variable. Because it is changing, that is why we say dx with respect to the changing time, dt. So for us to be able to observe the signal, we are now looking at how the signal is changing with respect to an independent variable. That is what brings us to differential equations. So you now see that when we begin to observe our physical systems, let's say let's assume you have a farm and you observe an apple falling from a tree. So there is a difference in the location while it was up there and it is falling. So by the time you observe that rate of change with respect to an independent variable, you have been able to describe the falling fruit or apple with differential equation. Does that make sense? So
yes,
this is just to make you recall Now let's clear this. The board is a little messy. Now, this is to make you recall that one notable mathematical method used for modeling physical systems is the differential equation.
Yeah.
Okay.
So,
Now,
sir, is it safe to say that time and space are our independent variables?
yes, time and space are independent variables.
Okay, sir.
Yeah,
Thank
they
you,
are
sir.
independent variables. Now, by the time we begin to, now look at it, everything we are doing right now, I'm in a location virtually and you're in another location virtually and we're interacting. Now, this class activity can equally be modeled using differential equations.
As a bilocation.
Exactly. So by the time we want to begin to discuss the relationship between what I'm saying and the time you get it, the latency, the delay in the network and all of that, how are we going to express that? We are going to be expressing that with respect to some independent variables in the system, right? And when we do that, we are actually trying to model the interaction using differential equations. That is why you see that there are some established authorities in the academic domain. This is where you are conducting your master's research or your PhD research, and they'll tell you, once you are able to describe the differential equations to model the problem you are trying to solve, you are done. You are done with your research. Because the challenge now is figuring out the variables that will describe the behavior of your system and how they are changing with respect to some independent variables. That is where the problem lies in system modeling. Whether you want to model the heat conduction in your electronic device, on your transformer, or your machines, or whatsoever. Now you are trying to vary some parameters with respect to some independent variables. And once you are able to address that problem and then establish the differential equation that describes that problem, you have been able to mathematically describe what is going on there. Now, what we have just established is that differential equations are not the only, does not form the only method, okay? Does not form the only, it's not the only mathematical method for modeling physical systems, but we just said it is one of them, okay? Because with differential equations, we are able to draw the relationship between dependent and independent variables. And once we do that, we are equally able to describe the rate of change in these variables. Okay? But we have other methods, like you already know. The state space model, where we don't have to use the differential equations, but this time we use the matrix method to resolve the problem. We also have the transfer function. Because with the transfer function, we should be able to synthesize the system, okay? Because we are able to tell the relationship between the output and the input. So with that, we are able to describe the zeros and the poles. You know, with that, we are able to also tell the system stability, okay? Depending on the location of the poles, you know, in either the S domain or the Z domain. So we're able to tell, is this system stable? So can we design it? Is it controllable? Is it observable? So with the transfer function, we can also model systems. And usually we use this in control system design, right?
Yes.
And then another method is the conceptual method. So why am I saying this? I just want you to know that differential equations don't form the only mathematical method, or it's not the only mathematical method for describing physical systems or electrical systems or some kind of system of interest. And here we have some, models, the unified modeling language, object modeling technique, information engineering, integrated definition for information modeling, okay? But our major emphasis is on the differential equations right now, okay? Because with this, we are able to talk about the rate of change, or the change occurring in the problem we are trying to solve, okay? And the ordinary differential equations govern the rate of change of system variables, okay? So this is what I just said. The ordinary differential equations govern the rate of change of system variables. And the function we wish to solve is actually in one of the independent variables, okay? So we know with the differential equations, we are able to describe the rate of change, and the ordinary differential equations literally governs this rate of change of system variables, okay? And one interesting thing I just mentioned is that the function we wish to solve for is in one independent variable for the ODE. Now, one of us just mentioned earlier that we consider one independent variable when we are trying to, when we are talking about ODEs, right? But what if we are trying to resolve problems for functions in two or more independent variables? Then we use the partial differential equations, right? So here we are considering one independent variable. So what if we have two or more independent variables? Then ODE, the ordinary differential equation methods, will not be a good fit for us. Then we'll have to consider the partial differential equations. Beautiful. Beautiful. So now I understand some of you, we really want us to begin to solve all of those Runge-Kutta, Euler, and all of that. For me, that is not as important as the theoretical basis, okay? Because, okay, we have Euler's method or the improved Euler's method. When should you apply it? How should you apply it? That's the problem. Now, it's a big problem. So you don't just want to apply it. So oftentimes we have some problems and we just, well, let's apply this numerical method. But that numerical method may not be the best fit for that solution, okay? For that problem. So, but understanding or grasping, the details relative to the theoretical basis will arm us with the necessary decision-making tools. Do you agree with that?
Yes.
Okay.
Very well, sir.
Okay. So now, if you agree with that, then I think we'll just move on. So when we talk about differential equations, we have two major groups, okay? Let's say categories of differential equations. So who can tell us these categories?
The ordinary differential equations.
Okay.
And the partial differential equation.
Partial differential equations.
Ordinary differential equation and partial differential equation.
Okay. Now, this sounds interesting. So I want us to clarify something again. Beautiful contribution. But let us clarify something. What is ordinary differential equation? What is ordinary differential equation? because you just mentioned ODE and PDE, right? What is ordinary differential equation? So we already
another
go ahead.
Another differential equation only involves one independent variable and one dependent variable. But in partial differential equation, you may have more than one
independent variables. Yes.
So can we say
multiple?
Now, can we say they form the categories of differential equations, being that we have described them with respect to some independent variables?
No, sir.
Perfect. So you just gave the answer. No. Okay, so what are the categories of
Categories could be, I guess, linear and non-linear.
Non-linear.
Okay, linear and non-linear. That's okay. Okay.
According to their order. Homogeneous.
Okay, so I'll just point this out. We have the initial value problem. I'm sure someone was thinking about this, right? And the boundary value problem. Okay, so when we categorize differential equations, we categorize them based on the initial value problem or the boundary value problem. Okay, so now we need to look this up. Okay, so you already know this. So when we say the boundary value and the initial value problem, what exactly do we mean? Yeah?
I think the initial value, you are given, you initialize the variables. So they have like the initial values they take on. Whereas boundary value, you have limits, like upper limits, lower limits.
Perfect. Good. So we can say that when all the auxiliary conditions are specified at the same value of the independent variable, and the solution is to be marched forward from the initial point, then we have initial value problem. And by the time we consider the initial point and the end point, like you said, or boundaries of the domain of interest, then we say it is boundary value problem. Okay? And here we have quite a number of methods, to address initial value problem and also to address boundary value problems. So, but this lecture is going to be based on the initial value problem. Okay? So, if this is going to be based on the initial value problem, then we see that the ordinary differential equation is of the order of the highest order of derivative, okay? And we usually designate it as probably the y, the x, being the same as f of xy, or we could designate it as the y, the t, as you may have it in some of your tests, the f of t, y. Okay? Now, in this case, the y, the x is the same as y prime, is the same as the y, the t, right? So, such that we could represent this as y prime being the same as f of sy, or y prime being the same of f of ty. Okay? And once we do this, we now have to establish the boundary value. We want to say, okay, f of s naught is the same as y naught, for instance. So that's the initial the initial condition. Or better still, we want to say y of t naught is equal to, say, y naught. Okay? As the initial condition. So this describes the initial value problem. And then we can also have the nth order ordinary differential equation, where we say a sub n, we have the polynomial plus a sub n minus 1, y of n minus 1, then plus a of n minus 2, y of n minus 2, all the way to a2 y prime prime plus ay1 y prime prime minus a naught y is the same as f of t is the nth order ODE, okay? Now, we are going to take things from a very simple perspective, okay? So I understand, you talked about the linear ODE, so in which its derivative appears in linear form and all of that. We have homogeneous differential equation, non-homogeneous differential equations, and all of that. Now, if we have the ordinary differential equation, for instance, before we begin to apply the solution, how can we be sure that there will be a solution? Okay, we have Ajiboye. Go ahead, please.
So the last on the nth order differential equation, we have y prime prime as the coefficient for the A1. Is that it or is that there?
What's that?
The y the A2 y prime prime plus A1 y prime.
Oh, sorry. That's prime.
Yes, that should be prime, sir. Thank you.
Prime. That's prime. Thank you for the observation. It is prime. Because the differential order is decreasing, right? Yeah.
Yes.
It is decreasing, yeah.
Yes, decreasing. Yeah.
Yeah. So thank you for the observation. So now, how can we tell if a numerical method will solve a problem? So we have an ordinary differential equation, for instance. So can we just go on to begin to apply some numerical techniques, or is there a way to confirm if there will be a solution or not? So we've given a background of differential equations, how modeling came about. We've been able to distinguish between dependent and independent variables. Now we've been able to define the ordinary differential equation, even to the nth order, okay? Now we need to begin to designate problems, okay? We've been able to see how we could model practical systems using differential equations, okay? Perfect. We've done these things for so many years. And some of us may have also lost touch of the analytical approach because we are now so used to the application of softwares, okay? So we just use softwares to run our programs and then we get our graphs and plots. But we are going to be playing with the analytical and numerical techniques, okay? So as to, maintain the balance. So before we apply any numerical method to solve ODEs, this is one thing you must do. You must confirm the existence and the uniqueness of the solution, okay? That is very important, okay? Existence and uniqueness of the solution. And the method that is used for this is the Picard-Lindelof theorem. Now, some materials also call this the Cauchy-Lipschitz theorem. So with this, we are able to confirm if the solution exists in the first instance, and if that solution we have a unique solution. Okay? So now, how do we apply the Picard-Lindelof theorem or the Cauchy-Lipschitz theorem? So if we consider the initial value problem that we specified earlier, y prime of x being the same as f of xy, given the initial condition s y of x naught being the same as y naught. Now here, f of xy is a function of x and y, isn't it? Isn't it? This function is a function of x and y.
Yes.
And
Yes.
now,
Yes, sir.
and now
Yes.
our y of x naught is the initial condition. Now, how do we tell that the solution is unique? Now, the solution is said to be unique in the region S naught, Y naught, if the following conditions are met. If the following conditions are met. So the first is continuity. We have to test for the continuity of the function f of xy. And this, once this test or this condition is met,
I'll have a lecture. I'm in a class. I'm in a class, please. I'm in a
then we
class.
are able to tell that the solution exists. Okay? So this tells the existence of a solution. Okay? So it means that f of xy is continuous within the range x naught, y naught. Okay? So it means that we must define a range. And by the time we compare the values in that range, if the polynomial exists, then we'll say that this solution exists. But the fact that the solution exists does not mean that there will be a unique solution. Okay? Because if we must have a unique solution, then it means that the solution must be bounded. Now recall your stability, okay, where you say Bible stable. So it means that a bounded input must give bounded output. So it means that the amplitude value of your input must be finite. And then the output also must be finite. But if at the end of the day, the output is infinite, then it is not stable. Okay? And then we will now say that there is no unique solution because it is diverging instead of converging. Does that make sense?
Yes.
So now, once we are able to confirm continuity based on the fact that there's a polynomial of that expression, then the next thing to do is to confirm for uniqueness, a unique solution. That is where the Lipschitz continuity condition is observed. That's in Y. So this Lipschitz continuity test ensures that there is a unique solution to the problem. So it means that it is bounded. The solution is bounded. It does not extend to infinity. Okay? And for this Lipschitz continuity test, so we can now consider a function, say f of xy is Lipschitz continuous in Y if there exists a constant, say L, let's use L. Some tests could use alpha. Some of the recommended tests use alpha, is greater than 0, such that the mod of the difference of the solution at these two different points, y1 and y2, is less than or equal to that constant value multiplied by this difference in the solution. Okay? And here we are considering this for all values of x, x1 range, and s, y2 range. Okay? We are considering for all of these ranges. So by the time we check for the solution at one point. Then we check for the solution at another point. Take the difference, the modulus of the difference, then that value should be less than or equal to the constant value multiplied by the difference in their solution. Now, the idea about this Lipschitz continuity test is to ensure that two solutions cannot diverge. Okay? So while we are looking up solutions in different steps, the idea is that two solutions in those different steps cannot diverge. And if that condition holds, it means that a unique solution is guaranteed. So let us verify this, this with a simple numerical example. Okay? So let's assume, okay, so how do we verify? So let's say how to verify that an ODE has a unique solution. So we just go through two major steps. So the first step is to check for continuity, as we said. We check for continuity of the function. So this is to ensure that the function f of xy is defined and continuous in the neighborhood around the region, okay? So it should be continuous within the region x0, y0, okay? For that range. And then the next step is to check for the Lipschitz condition. And for us to do this, it means that we have to calculate the partial differential, the partial derivative rather, of this function, f of xy. So it means that we have to differentiate with respect to y. Okay? So that is the f of xy dy. Now, if this solution is bounded, that is, it gives us a finite value. So it means that this must be less than infinity. So if it gives us a finite value, then it means it is bounded. Then this function, f of xy, satisfies the Lipschitz condition. And once the Lipschitz condition is satisfied, it means that we can have a unique solution. Okay? And then we can now go on to try any of the known numerical methods. Is that clear?
Yes, it is.
Okay. So let's look at one simple example. So let's assume we have an ODE given as this, s plus y, and then the initial condition is given as 1. So how do we check for continuity? So the first thing is to check for continuity, right? First, check for continuity. So by inspection, f of xy is the same as x plus y. And this is a polynomial, so it's continuous everywhere because it is a polynomial, right? So this is continuous. So once we vary the values, we see it is continuous everywhere. Very good. Because it is a polynomial. So it means that in this case, the solution
Guys,
exists.
please, let's mute now, please.
Okay? So it means that a solution exists, okay? Based on the fact that it is a polynomial. So a solution exists. But the fact that a solution exists doesn't mean there will be a unique solution. So we now have to check for Lipschitz. So the next thing is to check for Lipschitz condition. And that is simple. So we have to differentiate with respect to y. So if we differentiate with respect to y, so x becomes a constant. So that reduces to 0. So by the time we differentiate y, so that will give us 1, right?
Yeah.
So, and this one is a constant. It is less than infinity, right?
Yeah,
so it means it is bounded. So this ODE has a unique solution. So since it has a unique solution, we can try any of the known numerical techniques for solving ordinary differential equations, whether single step or multi-step technique to solve this problem, okay? But what if it does not have a unique solution? Let us try another example, okay? So we just, so we clear all that. So let us consider another ODE, y prime of x being the same as 1 over 1 over 3. And here, the initial condition is the same as 0. Now, the first thing is to check for continuity, right? First, check for continuity. Once again, this is continuous everywhere because by the time we vary the value of y with respect to the power of 1 over 3, it gives us a polynomial. So it's continuous everywhere. So a solution exists, okay? A solution exists, okay? Because it is continuous everywhere, okay? Hope that is clear. Now, so the next thing is to check for Lipschitz, right? So next, check for Lipschitz condition. And once we do this, the f, the y, is going to give us what? This is going to give us, okay, it's requesting to record.
3y is to the power minus 2.
Okay, we are recording.
1 over 3y is to the power minus 3.
So that's 1 over 3, y raised to the power of minus 2
over 3.
Yeah.
Okay, now there's a problem here because this is the same thing as saying 1 over 3, 1 over y, 2 over 3.
Y, 2 over 3.
So the problem is as y tends to 0, this parameter will tend to infinity. It won't be less than infinity. We tend to infinity. Because when y is 0, 1 over 0 is infinite value.
Yes.
Okay? So it means this system is unbounded. So there is no unique solution. Does that make sense?
Yeah.
So I may want to probably bother your minds and then bring up an ordinary differential equations that may not have a unique solution. And then you just begin to solve. And you see it keeps diverging. So what do you do at that point? It takes all your time, right? And then we begin to figure out what's the point? What's the point? Yeah.
Doctor.
Yeah, go ahead, please.
Doctor, can I come with a question?
Go ahead, please. Go ahead.
Now, once you affirm that a particular ODE does not have a unique solution, so what should be the conclusion?
Now, the conclusion is now is going to be based on is going to determine the method to use to address it. It does not have a unique solution. Does not mean it does not have a solution. It has a solution, but not a unique solution. Because at some point, you see that the iteration may be converging, then at some point it may diverge. So that may now border on the step size you are going to use in solving the problem, okay? So you may have to now figure out the choice of step size if you must have a stable system. Because the fact that this partial derivative extends to infinity implies that implies rapid growth of this expression, y, especially when y tends to 0. Okay, you get what I mean? So it makes this particular solution makes small differences in y lead to large changes in the function. So when we have small differences in y, we are going to have large solutions of f of xy. That may be a desirable concept depending on the system we are trying to design. Okay, probably want it to behave abruptly at some point. I don't know if you get what I mean, because there's high level of sensitivity in this system. So that sensitivity breaks the stability needed to ensure unique trajectory for the solution. Okay, so what you will now consider, let's assume you've modeled your system and you realize this is where you are at. Now, for some researchers, they want to perturb their metric to say, well, this thing is not converging. No, you don't have to do that. So at that point, you now have to figure out or investigate the particular method or the application of that response, because it is a highly sensitive system. You get what I mean? And that level of sensitivity could break the stability of the system. Okay, so what do you now do in a practical system that comes up with such abrupt behavior? You may want to put in some controllers, right?
Yes.
So it now informs the pattern of design, the dimension of design, and other complexities that may come in that process. You don't discard it. There is a solution, only that there is no unique solution.
Okay, sir.
Okay. Please, Doc, can you help me explain the first check again, the continuity of this function?
Okay, now the continuity of this function is that the signal is continuous, right? So there's no break. It's not discrete. Okay.
How do we determine that? Sorry.
How do we determine that? So let's say x is equal to y squared. So we can plot this graph, right?
Okay.
X, y. Okay, so sorry, y. Say y is equal to x squared. Let's put it that way. We have xy. So y is equal to x squared. So we have 1. So 1 squared is what? 1. We have 2. 2 squared is what? 4. Right?
4.
We have 3.
Yes.
3 squared is 9. So if we plot the graph, for instance, so this is my y. This is 2, 4, 6, 8, 12. Then this is my x. That's y. This is my x. This is 1, 2, 3, 4. So by the time I plot my 1 is the same as 1 here. My 2 is the same as 4. Right? So my 3 is the same as 9, somewhere around here. So by the time I plot this graph, it's a continuous line, right? It's continuous.
Yes.
Yeah. So,
okay.
So if you look at it, this is a polynomial. So by the time we vary this parameter with respect to the independent variable, we are going to get a continuous function.
That's correct, sir.
Yeah. So it means it passed the continuity test. So oftentimes, the ordinary differential equations may pass the continuity test, but they may not pass. They may pass the continuity test to show their existence. Okay, but they may not have a unique solution.
Solution.
Okay, so with the Lipschitz condition, we are able to tell that there will be a unique solution or there may not be a unique solution. Now, the fact that there will not be a unique solution does not mean we are throwing the problem away. It's just that the system will be highly sensitive, and such sensitivity could break the stability of the system. So we want to ensure that system operates within certain limits or range. Okay? So we also experience that in electronics, where we have to consider, especially for nonlinear systems, we want to look out for the linear range for operation. Especially when we are designing modulation schemes, to operate within a particular range. Okay? So at that point, we know that if we leave everything to just operate normal without some feedback and some control systems or controllers in the system, then the sensitivity of the system could just boom, and there may be, we may run into crisis at the end of the day when we begin to use that system. The same thing happens to some of the transformers that are imported. I don't know if things have changed. Back in the days, you see that transformers are designed to operate probably in a cold region. They are brought into Nigeria, and once we are in summer or the summer, you see they begin to blow up. because they are not able to.
It will explode, yes.
Yeah, when there is load with the external temperature and all of that, boom, they begin to blow up. So things like that. So it means that there's some level of sensitivity. So there are some conditions, that there are some criteria, or there are some components or elements or conditions that were not met in terms of designing that transformer for sub-Saharan Africa. You get what I mean? But let's assume,
yes, sir.
I understand most of you here are very big guys in the industry. So let's assume you are that big guy who got the contract. You want to quickly make some money. You tell them in China, hey, I need this. Or you go to the United States, I need this, or anywhere you want to get it. And you get it cheap. You bring them in, you install this commission. 2 months down the line, they blow up. Well, government will have to award another contract, isn't it? You get what I mean? So what I'm trying to say is that the system could be designed to operate within certain conditions. Once you observe the level of sensitivity of that system that could break stability. So getting to know the uniqueness of the solution, or if a unique solution exists, informs the design process and the choice of numerical method or technique to use. Is that okay?
Yes, sir.
Okay,
yes,
so
sir.
now another thing I want us to quickly look up before we begin to talk about the exact numerical methods we are to consider in this lecture are some critical measures we use in evaluating numerical methods, okay? So let's wipe this. So I call these critical measures when evaluating numerical methods. So now, well, for ODEs, let's just put it that way, not just numerical methods, for ODEs, for ordinary differential equations, since that's what we're talking about. So the first thing is accuracy. We want to ensure accuracy, okay? So another thing is stability. We already mentioned stability, so we'll just mention it here again. Then another thing we want to look up is efficiency. Okay, so how does this metrics play in? Now, when we talk about accuracy, this is the measure. Let's put it, okay, this is the measure of how close the numerical solution is to the exact solution. Okay? So usually when you have an ordinary differential equation, there's usually an exact solution, okay? Which you can solve analytically and using your integration by part and all of that to address, to say, well, this is the exact solution. So once you plug in the parameters, you know what the value should be. But the idea about numerical method is that it always deviates from the exact solution. So let's assume the exact solution is 1.2. Now, the numerical solution may give you 1.1. It may even give you 1.09, okay? Now, this may go on. It may even give you 1.002, while it comes close to 1 point. Now, it could come to 1.12, okay? While it comes close to the exact solution. So what we are talking about here is that the measure of accuracy is to figure out the difference between the exact and the numerical.
The solution.
So this brings us to error estimation. Okay? And we have two, the local truncation error and the global truncation error. Okay? So here we now talk about the local truncation error and also the global truncation error. Okay? So when we consider the local truncation error, we are actually considering the error introduced in each step. So let's assume we have 1, 2, 3, 4 steps in this iteration process. So what is the error introduced in this step? That's the local truncation error. Then we now check the error introduced in this step, in the individual steps, okay? And once we do this, we now see that the local truncation error is usually proportional to the step size, okay? So if, for instance, the step size is h, now h raised to the order of the method being used, where p is the order, okay? Then that gives us the order of the error for the local truncation error. So here we say step size, why this is the order of the method. Okay, it could be Euler, it could be Runge-Kutta, it could be improved Euler, it could be midpoint, you know, it could be anything. But when we now consider the global truncation error, we are looking at the cumulative effect of the local truncation error over all the steps. So we now want to consider, okay, here I can see Latif request, okay, yeah, so we're already recording, so you don't worry. So now you see that, but we now want to consider the effect of this error, the cumulative effect of all of these local truncation errors gives us the global truncation error. And usually, yeah, the global truncation error. And this usually is described in terms of the order h, p minus 1, where h is the step size, and p is the order of the method used minus 1. So when we begin to use Runge-Kutta and some of the implicit and explicit method, let's put it that way, then we now begin to see, oh, what's the order of error in this system? Yeah. Okay, so we can tell. So that's to measure the accuracy, because we don't just want to use any method. That's why you see that Runge-Kutta, the fourth order Runge-Kutta is preferred in terms of the accuracy. But not that the sixth order or the seventh or the 10th order Runge-Kutta method will not give us better accuracy, but it comes with more complexities because we now have to deal with more variables. You get what I mean? So there's a trade-off between accuracy and complexity in terms of implementation. So we just stick with Runge-Kutta fourth order most of the time, in most of the practical systems. You get what I mean? So if you now want to adopt the nth order Runge-Kutta method, for instance, for improved accuracy, then there are other things you now want to look up also, the complexities and all of that. So there's usually a trade-off. Now, when we talk about stability, the stability actually refers to the method's ability to control these errors. So we want a method that will be able to control all of these global local errors and yet produce a bounded solution for long-term simulations of stiff equations. Okay? And then we can go on to begin to describe some other activities and all of that. And then, what else now? Yes. And then for the efficiency, well, when we talk about efficiency, we want to ensure how do I put it now? The usefulness of the system we are actually playing with. Okay? And then how it plays out in actual application. Okay? And here we'll have to now consider the efficiency in terms of the steps. So the method we want to use. We have the single step method, the likes of your Runge-Kutta, Euler, and all of that. Then we also have the multi-step method, okay, where we have the what's it called now? The Adams-Moulton method, and we also have the backward differentiation method, you know, formula and all of that. So the efficiency for multi-step methods are more like efficient for large problems. When we want to look at large problems, then we cannot use the likes of Runge-Kutta to solve those problems, okay? Because we have to reuse a lot of information. But the single-step methods are simpler to implement, and then we prefer them for simpler problems. So that's where we begin to talk about all of those Runge-Kutta and all of that. But when we begin to look at very large problems and we have to reuse, because at that point, the performance of the methods like Runge-Kutta, the fourth order will not be efficient. Okay, so we now have to consider some other techniques. Now, I'm just trying to run through all of this. So if you look up the reference materials, you'll be able to, gain, in-depth analysis as far as these things are concerned. Okay. Now, before we begin to talk about these single-step and multi-step methods, let us talk about implicit and explicit methods. So who can tell us what we mean by implicit and explicit methods? Implicit and explicit methods. Okay, now this is it. The implicit and explicit methods are the two fundamental approaches used for solving ODEs. So your Euler method, your Runge-Kutta, your Adams-Bashworth method, they all fall within this implicit or explicit. Okay? And both of them differ based on how they compute the solution at the next time step. Okay? So you see that there are some solutions where y of n plus 1 will only compute based on the previous step. Okay? So it cannot compute based on the step, on the new step. So such techniques are called explicit methods. Okay? While there are some other methods that when they want to compute, when you want to compute the next step, you may have to also compute that step, that same step. So why this is explicit, like you have been playing with your Runge-Kutta and all of that, this is implicit. Because the solution at the next step, which is this step, is determined by solving an equation that also includes the same step, the same step. Okay? So here, we don't do analytical activities. This is usually iterative. Okay? And some of the methods for this explicit method are the Euler method or Euler's method, the Runge-Kutta method, even the Adams-Bashworth, Bashworth, and all of that. Then for the implicit method, we have the backward Euler method, which is an implicit method. And you see that the update is given as y sub n plus 1 being the same as y sub n plus h of f, xn plus 1, yn plus 1. This is the backward Euler method. Why the Euler method, which is an explicit method, is simple and straightforward, which is yn plus 1 being the same as y sub n plus h of f, xn, yn. You get what I mean? So you see that for the explicit method, we rely on the solution to the previous step to solve
the previous
step. Yeah. But for the implicit method, we need both the previous and that present step to get the solution. So we now have implicit, there's implicit Runge-Kutta method. There's the Adams-Moulton method. Okay, and so many other methods you should be able to. So now this forms the broad classification of methods that can be used to solve ordinary differential equations. Okay, so let us now come down to the business of the day. So we spent quite some hours just trying to build a background. Yeah, go ahead, please.
Apologies. I just wanted to confirm, where does the Gauss-Seidels and the Nutter-Rabsint method fall from that? The iterative.
Okay, you know, when we are dealing with linear solutions and all of that, then we begin to play with all of those Jacobian and all of that. So I think you will do that in your numerical methods too. We won't consider them in this numerical methods one. Your Gauss-Seidel, Jacobian, and all of that. So you are going to consider them in numerical methods too. Okay, so in numerical methods one, we are just streamlined to ODEs, PDEs, spline function, approximation of functions, numerical integration, and what else? Yeah. Okay, so that's another interesting half of the numerical methods to form a complete basis for your numerical methods. Yeah, but that will be covered in numerical methods too. Yeah. I think the coordinator himself will be taking that. Okay?
Okay, sir.
Yeah. Okay, so now let us come back to the initial value problem. What are the solutions for the initial value problem? Okay, so these are things you already know. So solution, methods for initial value problem. Recall we mentioned that we have the initial value problem and the boundary value problem. And what we want to look up here is the initial value problem in this lecture. So in another lecture, we'll look up the boundary value problem. So for the initial value problem, we have two broad categories of methods, the one-step methods and the multi-step methods, okay? So we are now going to run through these methods, you know, in, will I say in a flash? Okay, yeah. So I think I want to use straight line here. So let's say this. So I said we have two broad categories. One-step method and multi-step methods. Okay, so for the one-step methods, there are methods you already know, which happen to be the Euler's method. We also have the higher order Taylor's method. Then we have the Runge-Kutta methods. The idea is that the Euler's method and the higher order Taylor's method forms a group of analytical methods. These are analytic. And why the Runge-Kutta forms numerical method, numeric. Okay, so we'll come to that later. Now, for the multi-step, we have the Adams-Bashworth. Then we have the Adams-Moulton method. Then we have the Predictor-Correction methods. And we say that this actually forms the fixed step methods, okay? And then still under the multi-step methods, we have the Graggs method of interpolation. And also the Fehlberg's method of step size adjustment. And these two forms variable step methods, okay? So these are the broad categories, okay? And we'll just run through their formulation, okay? So the point is, when we talk about the Euler's method, it's one step at a time, right? So, but when we now have to consider multiple steps at a time in each iteration, then we use the multi-step methods. So with this, I'll just run through the formulation and then leave a whole lot as assignment for us, okay? So I think that will be so much for one lecture, isn't it?
Yes.
Okay. So let us look up the formulation of these methods, okay? So now recall for the ODE, so we are considering, okay, let's just put that. So let's consider the ODE, the ordinary differential equation y prime of x being the same as f of xy when the initial condition is the same as y naught. Now, we already know that y prime of x is the same as dy dx, right? So that has been taken care of. So let's look at the single step methods, okay? Methods. So I think I need to split the board so we are able to manage what we have here. Okay. So, so we have the first, the Euler's method, for instance. So we have the update given as the initial point plus the step size times the function given the initial point. So here, h is the step size, okay? Now, usually this is also referred to as the first order Runge-Kutta method, okay? They also address this Euler method as the first order Runge-Kutta method. Okay, so I will leave that at that. Then we have the modified or improved Euler's method, okay? Also referred to as the second order Runge-Kutta method. And here we have the update given as 1/2 of the step size. Then we have to estimate the function when we have the initial or the previous values. Then plus, okay, with this ticket, I need to wipe this then. Let's take this out, okay. The function s of n plus 1, y sub n plus h of f, xn, comma yn. Okay, here h is also the step size. And this is also referred to as the second order Runge-Kutta method. Now, if we now have to address it as the second order Runge-Kutta method, then we want to rewrite this expression to say K1 is the same as h f of xn, yn. Then K2 will be the same as h of f, Sn plus h, comma, yn plus K1, such that the updates will be the same as the previous value plus 1/2 K1 plus K2. Okay, so this is the same as this, as the improved Euler's method, okay? Now, then the formulation for the midpoint. Let's look at the midpoint before I go to the third order Runge-Kutta method. Okay, so so you have nothing to worry about. You get the videos, okay? We'll upload them. So for the midpoint, method, we have that the update is given as y sub n plus h dot f Sn plus 1/2 of the step size, then yn plus 1/2 of the step size f of Sn yn. Then that's the third, still on the single step methods. Now, the fourth here is the third order Runge-Kutta method, which is the Bogacki-Champagne or Champagne method, which is the third order Runge-Kutta method. Here, K1 is the same as HF, Sn, Yn. K2 is the same as HF, Sn plus 1/4 H, Yn plus 1/4 K1. Then K3 will be the same as HF, Sn plus 3/4 H, Yn plus 3/4 K2, such that the updates of the present value will be the same as the sum of the previous value plus 1/6 is 6, K1 plus 2/3, K2 plus 1/6, K3. And here, the local truncation error is the same as h to the 4, and the global truncation error is the same as h to the 3, right? So where we say the order of h to the 3, right? Recall the formula of HP minus 1, right? So, yeah. Now, okay, so this is the formulation for the third order Runge-Kutta method, which we also address as the Bogacki-Champagne method. Then let us look up the popular fourth order Runge-Kutta method, okay? The fourth order Runge-Kutta method, which is usually preferred in most of your analysis. So we have K1 being the same as f of Sn, Yn. Then we have K2, which is the same as f of Sn plus h/2, Yn plus h/2, h/2, K1. Then we have K3 being the same as f of Sn plus h/2, Yn plus h/2 K2. Then K4 being the same as f of Sn plus h, Yn plus h dot K3. And then the update plus 1 will be the same as Yn plus h/6, which is K1 plus 2K2 plus 2K3 plus K4. Now we can go on and on even to the nth order, okay? So let's assume we want to represent the nth order Runge-Kutta. So we know K1 is h of f, Sn, Yn. Then K2 will be the same as HF, Sn plus A2, where A2 is a coefficient, H, Yn plus B21 K1. And then we have K3 will be HF, Sn plus A3H, Y plus B31 K1 plus B32 K2. So we're going to go on and on till we get to Kn, which is the same as HF, Sn plus ANH, Yn plus Bn1 K1 plus Bn2 K2 all the way to Bn, n minus 1 Kn minus 1, such that the update will be the same as Yn plus 1, being the same as Yn plus sigma I taking on values from 1 to n, alpha I, ki. So here you observe that the coefficients alpha I, a sub I, and bij are carefully chosen such that the method achieves the nth order accuracy. So the values are not placed arbitrarily, okay? Okay, so I think that's for that. So for the one-step methods, then we just look up for the multi-step, and then I think we can call it a day for today. Multi-step methods, the formulation. So we have the first, the Adams-Bashworth method. This is an explicit method anyway. So these methods use previously computed values, okay, to estimate the initial value. So let's take, for instance, say we want to consider two-step because it's multi-step. So then what we have for the Adams-Bashworth is y sub n plus 1 as the initial new step, then n, that's the initial step, plus h over 2, 3f, Sn, Yn, minus f, Sn minus 1, Yn minus 1, okay? Now, if we consider 3 steps, we could consider n step for the Adams-Bashworth method, but let's say we consider 3 steps, so that would be Yn plus 1, same as Yn, plus h over 12, this will be 23, f, Sn, Yn, minus 16, f, Sn minus 1, Yn minus 1, plus 5, f of Sn minus 2, Yn minus 2, okay? So that's that for Adams-Bashworth. So, which is an explicit method. So let's look at Adams-Moulton method, which is an implicit method for multi-step methods. So the second for this, which is Adams-Moulton method. So this is an implicit method. So the methods require solving equations iteratively, like we mentioned earlier. So let's consider one step, for instance, which is usually referred to as the trapezoidal rule. Trapezoidal, I missed the P. Trapezoidal rule, okay. So the update will be n, y sub n plus 1, which is y sub n plus h over 2, f of xn, yn, plus f of Sn plus 1, then Yn plus 1, okay? Then if we consider 2 steps, for 2-step, then that will be Yn plus 1, will be the same as Yn, plus h over 12, 5 Sn plus 1, Yn plus 1, plus 8f Sn, Yn, minus f of Sn minus 1, Yn minus 1, that. Okay, so I think we are good. There's just one I will mention, then if you have any question, we take it. Then that is the backward differentiation formula. Which is a multi-step method, okay? It's popular, BDF, okay? So it's also an implicit method. So it's an implicit method, So if we consider one step, it's pretty straightforward. We call this the backward Euler method. So we have Yn plus 1. The same.
Good afternoon, sir.
N plus h, f, Sn plus 1, Yn plus 1.
Afternoon, sir.
Yeah, a very good afternoon. Just 1 minute. I'm almost done. So if we consider 2 steps, so 1 over 2, Yn plus
Okay, good afternoon, sir. Good afternoon, sir. Sorry, I was muted.
plus 1 over 6, yn minus 1 being the same as h of f, Sn plus 1, comma yn plus 1. Okay, so I think these are some of the methods. So I think the next thing would be to look up some numerical examples to see how they are used to solve some of these problems. Okay, just needed to put up their formulations, because when you look up some of the tests, some of the reference tests, a lot of derivations and a few things may not be as straightforward, but I hope the analysis presented here will make things a little easier when
Please, Doc.
you have to.
Yes. Yeah, thank you. You've done it. That's what I wanted to ask. Why n plus 1?
Yeah. Okay, so any question, please, before we call it a day for today? It's been about 2 hours already.
Yeah, good day, sir.
A very good day.
Thank you for the wonderful lecture. May God Almighty Allah bless you, sir.
Amen.
Please, can we really get some reference text that will still guide us a bit?
Yes.
Okay, sir.
I mentioned them in the teaching plan, so I'll forward the teaching plan to the WhatsApp group.
Good afternoon, sir.
Yeah. So
okay,
you
sir.
can download.
So, rightly, like you have said, sir, and as I mentioned, I and Mr. Ahmed were in contact yesterday, because we're facing
Well, we can hardly hear you. Are you addressing us?
Just shared the picture with me on the group.
Mute your video and give us audio.
Okay.
On my end, like externally, outside of the WordPress environment. And I shared this with Mr.
I don't think he's talking to us, so someone should mute him. He's not talking to us.
He later told me that I'd have to clear my cache.
Yeah, can you mute him, Bob? Can you mute him?
Okay.
Put that guy on mute.
Okay. I think we've done that. Okay, I think we've done
Hello,
that.
sir. I have a question.
Okay, go ahead, please, with your question.
Yes, my question is all these formulation for the method used in explicit and explicit. Are we to know it? Yes, implicit. Are we to know it step by step, or I don't know how I'm going to be applying it? Thank you.
Yeah, I think my intention was to solve some numerical examples using all of these steps to see how it applies, but we already ran out of time, and taking you beyond your normal weekly 2 hours, I don't know how you take it. You may also feel saturated. So what I'll do, if we will have to revisit this, then we'll look up some examples. If I feel we may not have to revisit this, then I'll try to solve some of those examples and upload them to the channel so you could look them up while we progress.
Okay.
Because I understand some of you.
Different, sir.
Okay. So I understand some of you are running out of time and you just need to get this course done with, take your assessment so you could get your certificate. So on that ground, I don't think we want to spend too much time dwelling on most of the concepts. So once you understand the concepts and you are able to apply them, we are good. So
okay, sir.
Yeah, there are some methods we may not be able to apply analytically. So the MATLAB software or Python programming will help us apply those methods because of the complexities and the rigor. Okay, so we'll get to know that as we begin to look up some examples.
Yeah, question, quick one. The issue of using the MATLAB software and the Python, are we advised to get MATLAB ready for such solution?
Exactly. You should have MATLAB ready. You should also have your PyCharm ready for Python. And I'll suggest you begin to play with them already. I understand you are doing computer-aided design, so I'm sure they'll be teaching you how to use your MATLAB and other programming tools to solve engineering problems. And if not, it would be good you try to get a little used to using them. But if you already know how to use them, well, it's good. That would be an added advantage. So in this course, as we try to manage the time, we'll also try to use some of those applications to solve some of the problems. So you see how they apply, because there are some keywords or functions that are used, that are, used in MATLAB and the likes, the ODE activity, and so a couple of them. So we'll play with them. We'll play with them.
All right, sir.
Okay. Okay. So any other question? Okay. So in the absence of none, I will also encourage you to subscribe to the channel so you are able to get notified each time I upload any new video. Okay. And then
Okay, sir.
and then try
Okay,
to
sir. Thank you, Will.
look them up. And
Okay, thank you, sir.
I'm sure.
Thank you very much, sir. We are grateful.
Okay, it's okay. So that's fine. So hope to enjoy the rest of our moments together taking this course. So do have a great day.
And you too, sir.
And you too, Doc. Thank you, Doc. Thank you.
Bye, sir.
Thank you, everyone.
Thank you, sir.
Thank you, sir.
You're welcome.